This time we're going to talk about how to find and fix problems with floating point computations. We saw one class of problems in the last video, which is cancellation. I'd like to go through a handful of other problems that do occur frequently in real computations of different types. So the bad news with all of this is floating point arithmetic and real arithmetic are not quite the same thing. There's just a little bit of difference, and sometimes it can bite you. Now the good news is floating point arithmetic is a pretty good approximation to real arithmetic in many ways. You're guaranteed to have 16 digits of accuracy in basic operations, assuming no overflow and underflow. And furthermore, some things are done exactly. For example, integers are represented exactly. If you subtract two numbers which are within a factor of 2 of each other, the difference is computed exactly. And if you scale a number by 2 or by a half, that's computed exactly, barring over or underflow. Those are types of properties that somebody who is really being careful with floating point arithmetic can exploit in order to do cool things. I'm not going to necessarily ask you to exploit these things, but I do hope that if you're ever in the position of writing a compiler, say, you will realize that people like me do use these properties sometimes and won't screw them up for me. So things can go bad, but the floating point system has its own set of nice properties, and we can usually fix things that are going wrong when they do go wrong. So let's see how some things can go wrong and what we can do to fix them. We talked in the last video about cancellation. So for example, suppose that z is much less than 1, a positive number, maybe on the order of 10 to the negative 20. I want to compute 1 minus the square root of 1 minus z. Now, that's going to suffer cancellation, and it's actually going to look like 0 according to this computation. A better way of phrasing the same calculation is y is equal to z over 1 plus the square root of 1 minus z. Now, this looks like a fairly arbitrary expression, but actually if you try to write down calculation of pi based on the semi-perimeters of polygons of size 2 to the k, for k increasingly large, you run into exactly the difference between these two expressions. This is a sub-expression that occurs in that computation. If you're interested in details, you can look at the version of 3220 that I taught last spring, in spring 2011. And the lecture notes in the first lecture describe this calculation. Now, another thing that can go wrong is that you have a subproblem which is very sensitive. So consider the code that's shown on the screen. I start with the number 2, I take the square root 60 times, I square 60 times, and then I display the result. Right? Now, if this was real arithmetic, what came out would be 2. That's not what comes out. I will leave it to you to run this example and look at what comes out. Try to explain why. I will note that what happens can be explained purely in terms of a single rounding error. So the first loop produces the correctly rounded result. The blame lies purely in the sensitivity of the calculation represented by the second loop to small perturbations in the input. We did this one a couple of videos ago. So this is a way of computing the integral of x to the n times e to the x minus 1 dx. Right? And we know from a little analysis that the numbers produced by this recurrence should be less than 1 over n plus 1. But if you actually run the recurrence on the computer, you'll see that things go completely nuts around n equals 18 and 19. So this is an example of small errors in the input being amplified. It's a variant of the previous example, if you like. This one is more subtle because this is one that you might think was absolutely fine. So suppose that I do the following, right? So I have 2 dice. One of them is slightly unfair, so it rolls heads with probability 1.001 over 6 rather than probability 1/6. Okay, so you pick one of the dice from my hand, and you roll it, and it rolls ones 415 times in a row. So what's the probability that you pick the fair dice? Now, this is a fairly straightforward exercise in Bayes' rule. So the probability of 415 ones given the fair die is 1/6 to the 415. Given the unfair die is 1.001 over 6 to the 415. And so I can compute what the probability is. It's a simple formula. There's a slightly trickier formula shown below. And what you'll see is that those two things give very different answers. One tells you that the answer is about a third, the other one is 0.39. So that's an error in the second digit. What goes wrong? Well, you wouldn't be able to tell if you tried to analyze this using our standard model. And the reason is because this is a place where the standard model is violated. And the reason it's violated is because the probability that we're talking about is so small that it falls below the underflow threshold. So we're working with subnormal numbers and we lose precision. Now, we got a little bit unlucky in this case. If I had chosen 420, the first calculation would have returned a nan. You would then know at least that something has gone wrong. But it's a little bit disturbing that you can lose a lot of precision with an apparently fine calculation, not necessarily realize that something has gone wrong. So underflows are another thing to watch out for. Branches can be a little bit tricky if you're used to the idea that things are positive or negative or zero, and those are the only possibilities. And the reason for that is because floating point arithmetic allows this possible not a number. And comparing anything to not a number in any way is false. So if I look at the code shown on this slide, what do you think the output will be? If you're not sure, I suggest trying it and seeing. It's a little bit counterintuitive at first. In each of these examples, we've seen something that resulted from a slight discrepancy between the way floating point arithmetic works and real arithmetic works. Now, none of these things are difficult to get around. We can write branches differently, we can analyze recurrences for sensitivity, we can do all sorts of things like this. Slight changes in formulas often fix them very nicely. The point is that you need to be aware that these things are possibilities. This is not the end-all and be-all of scientific computing, but it is a useful thing to know about.